We are in Statistical Rethinking, second edition, and we're just starting chapter 14. And in these last few chapters here, 13, 14, 15, there's some very exciting tools that are taught in the book. And in this particular chapter, we are looking at, in the previous chapter, in chapter 13, we were looking at how to build like hierarchical models, and I think that chapter was called Models with Memory, where we could put these adaptive priors in place, hyper priors or hyperparameters. And now we take that concept one step further, where as previously we might be estimating, making separate estimates for the different parameters, we will now begin to look for relationships among parameters. Okay, so if that seems a little bit confusing, I encourage you to go back and reread the introduction to chapter 14. I think it gives a fairly good intuition as to when this might be appropriate or useful. But we're just going to jump right in with 14E1. And in 14E1, we are supposed to add varying slopes on the predictor X, okay, on this model. Okay, so here's the model, and we have to modify this somehow. Okay, so here we have X, and so we need to add varying slopes to this beta here. Okay, well, now the most basic way that we could do this is just to simply modify the model to where we're estimating a separate beta for each group. Okay, and then each beta would get its own distribution here. Okay. But we could possibly make our model more powerful, or at least have more out-of-sample predictive power, if instead of estimating completely separate beta coefficients for each group, we instead partially pooled that information, right? So that each one of the beta coefficients was coming from a larger distribution of possible beta values. Okay, and so this is really what the last chapter was about. Okay, and so we could build a hierarchical model where again we continue to modify the model, but now instead of just having a prior for the beta for each beta, our prior for each beta, beta for each group itself comes from a larger distribution that has a prior of a normal being beta and sigma beta, and then of course each of those would get their own priors. Okay, and now this chapter goes one step further and says, well, what if there is a relationship between the alpha and the beta parameters? Okay, and so now we're looking for relationships between parameters, not just within a parameter, okay, or levels of a parameter. And so this is how we begin to deal with this. And so this is, you can kind of get a sense of this in section 14.1. But we have our model, okay, and we've added our varying intercept and slope, okay, for each group, okay. But now we're saying that there's a relationship between these, okay, and so if you go back up, we said that alpha and beta were themselves normally distributed, okay, and so that's suggesting that we can wrap these together into a single distribution, a multivariable normal distribution, which I am denoting here as normal with a subscript 2 to denote that that this is multivariate normal with 2 dimensions, I guess. Okay. And so now my varying intercept and varying slope, they get packaged as this vector right here, and we're saying that together they form a multivariate normal distribution with a mean vector of alpha beta. Okay, and so where does that alpha beta come from? Well, so we already had the prior for alpha group, which was alpha, right? And then we built the prior for the beta group, beta. Okay. All right. And so a multivariate normal distribution has a few components. One is the mean vector, right? What is the mean value of each of the elements therein? And then also the variances and covariances among the elements here, the parameters alpha and beta. Okay, so we need to build this covariance matrix, okay? And so we can do that in this way. Okay, this is how it's demonstrated in the book, where let's to get a sense of this, let's just ignore the R here, and so we're just going to multiply this matrix by this matrix. Okay, and so what do we get? Well, if you take the sigma alpha times sigma alpha plus 0 times 0, you just get sigma alpha squared. Okay, and then hopefully you understand matrix multiplication. I didn't really go through the steps of showing you how to do matrix multiplication, but then if we do it to the next element, we have 0 times sigma alpha plus 0 times sigma beta. Well, that's just 0. And if we go here and here now, that's our next multiplication. We go sigma alpha times 0 times beta times 0, sigma beta times 0, we get another 0. And then finally, we go here and here, so 0 times 0 plus sigma beta times sigma beta, that's sigma beta squared. Okay? And so then what we have is just a diagonal matrix where the variances, sigma squared alpha and sigma squared beta, are in the diagonals. And so that would be if alpha and beta had no relationship at all, right? They were completely independent. But if they have any relationship, then we would need to have the off-diagonal terms be non-zero. And the way that we get those non-zero off-diagonal terms is with this R matrix here. Okay, and so I won't go any further into that because I feel like I'm just speaking words and possibly confusing people. But this R matrix is going to represent the relationships, the correlations among the parameters. And so when you do the matrix multiplication, you get out a covariance matrix that has the variances along the diagonal and then the covariances along the the off diagonals. Okay. So anyway, so we have our priors for alpha and beta here, or our hyperparameters. Okay, and then we have S. Okay, so we're defining S as this, and S itself has its own parameter here that we have to estimate called R. And R is going to be, it's going to be a matrix like we just discussed, and we can set a prior called the LKJ correlation, or just the LKJ matrix, I think, with a prior of 2. Hopefully there are questions later that explore this matrix, and if not, I may do a separate video about it because it's a very interesting and useful concept. Yeah, so anyway, and then we also have our priors for the 2 sigma alpha, sigma beta. Okay. All right. I think that is it, and we will see you in the next one.